The night sky has always held a certain fascination for humanity. Are we alone in this vast expanse? Is there another Earth out there, teeming with life, or are we a solitary spark of consciousness in an otherwise silent universe? These questions have haunted our philosophers, driven our scientists, and inspired our artists. We've sent probes to distant planets, listened for whispers from the stars, and pored over data in search of even the faintest hint of an answer. But the 21st century has ushered in a new era of exploration. Advancements in astronomy, astrophysics, and computer science have given us unprecedented tools to explore the cosmos. We've discovered thousands of exoplanets, many of them located in the habitable zones of their stars. And now we have a new ally in our quest for answers. Artificial intelligence, AI, with its ability to process vast amounts of data, identify patterns, and make predictions, has the potential to revolutionize our search for extraterrestrial life.
One such AI that's making waves in the scientific community is ChatGPT-o1. Developed by OpenAI, ChatGPT-o1 is a large language model with a remarkable ability to process information, understand context, and generate human-like text.
ChatGPT-o1's involvement in the search for extraterrestrial life is not about replacing human scientists or diminishing their role. By working in tandem with AI, we can push the boundaries of our knowledge and move closer to answering the age-old question, are we alone? Before we dive into the mathematical probabilities of life beyond Earth, it's crucial to grasp the sheer scale of the universe we inhabit. Our planet, a tiny oasis of life in the vast cosmic desert, is but one of 8 planets orbiting an average star we call the Sun. The Milky Way, a barred spiral galaxy containing hundreds of billions of stars, is just one of billions of galaxies in the observable universe. Each of these galaxies, some larger and some smaller than our own, contains billions upon billions of stars, many of which likely host their own planetary systems. Yet the very immensity of the universe, the sheer abundance of stars and planets, also gives us hope. In a cosmic lottery with trillions upon trillions of tickets, it seems statistically improbable that ours is the only winning number. Let's try to put some numbers to this vastness, even though our minds struggle to truly comprehend such scales. The Milky Way galaxy, our cosmic home, is estimated to be about 100,000 light-years across. Within the Milky Way, there are estimated to be between 100 billion and 400 billion stars. The observable universe, the portion of the cosmos we can see from Earth, is estimated to contain trillions of galaxies.
As ChatGPT-o1 succinctly puts it, the vastness of the universe suggests that even extremely rare events are likely to occur somewhere. In a cosmic game of chance, with trillions upon trillions of rolls of the dice, it would be remarkable if life on Earth were the only outcome.
It's important to acknowledge that the numbers we're dealing with here are almost impossible for the human mind to truly grasp. We can talk about billions and trillions, but these are just abstract concepts. But even if we can't fully comprehend the immensity of the universe, we can still appreciate its awe-inspiring grandeur. The vastness of the universe should fill us with a sense of wonder and humility. It should remind us that we are just a small part of something much larger than ourselves. A cosmic tapestry woven from stardust and shaped by forces beyond our comprehension. And perhaps, just perhaps, this vastness holds the answer to one of humanity's most profound questions. Are we alone? In 1961, astronomer Frank Drake devised what is now known as the Drake equation. This equation, while not intended to be a definitive calculation, provides a framework for estimating the number of detectable civilizations in our galaxy.
The Drake equation, in its elegant simplicity, considers a series of factors that would influence the likelihood of finding intelligent life. It starts with the rate of star formation in our galaxy, a number that speaks to the sheer abundance of stars in the Milky Way.
The equation then delves into more speculative territory, considering the fraction of those planets that could support life, the fraction of those where life actually emerges, and the fraction of those where intelligent life evolves.
Finally, the Drake equation considers the fraction of intelligent civilizations that develop technology capable of interstellar communication and the length of time such civilizations release detectable signals into space.
While the Drake equation provides a framework for estimating the number of detectable civilizations, it's important to remember that the values assigned to each variable are largely speculative. This is where ChatGPT-o1, with its ability to process vast amounts of data and identify patterns, comes into play.
When fed with the latest astronomical data and scientific models, I can help refine our estimates for each variable in the Drake equation.
By running multiple simulations with varying values for each variable, ChatGPT-o1 can provide a range of estimates for the number of detectable civilizations in our galaxy.
It's important to note that while I am a powerful tool, I'm not a crystal ball. I can't provide definitive answers to the question of extraterrestrial life. However, I can help us ask better questions, refine our hypotheses, and focus our search efforts.
The beauty of the Drake equation, even with its inherent uncertainties, is that it opens our minds to the vast possibilities of the cosmos. Depending on the values assigned to each variable, the equation can yield estimates ranging from a handful of detectable civilizations in our galaxy to millions or even billions. Even if we take a conservative approach, assuming that the conditions for life are extremely rare and that intelligent life is even rarer, the sheer number of stars and planets in our galaxy suggests that we are unlikely to be alone. As Carl Sagan famously said, the universe is a pretty big place. If it's just us, seems like an awful waste of space. The Drake equation, as interpreted by ChatGPT-o1, doesn't provide a definitive answer to the question of extraterrestrial life, but it does offer a tantalizing glimpse into the possibilities. It reminds us that the universe is full of wonders yet to be discovered, and it fuels our desire to explore the cosmos and unravel its mysteries. Our search for life beyond Earth often focuses on finding planets similar to our own, rocky worlds orbiting within the habitable zone of a sun-like star, where temperatures are just right for liquid water to exist on the surface.
Enter extremophiles, organisms that flourish in conditions that would be lethal to most other life forms. These hardy creatures have been found in the depths of the ocean, near volcanic vents spewing scalding water and toxic chemicals, in the dry, frigid valleys of Antarctica, and even within the radioactive rocks deep beneath the Earth's surface.
Tardigrades, often referred to as water bears or moss piglets, are perhaps the most famous extremophiles. These microscopic creatures can survive being frozen, boiled, dried out, exposed to the vacuum of space, and bombarded with radiation levels that would kill a human 1,000 times over. They are, without a doubt, some of the most resilient life forms on our planet. The discovery of extremophiles on Earth has profound implications for our search for life beyond Earth. It suggests that life is far more adaptable and resilient than we once thought, capable of surviving in a much wider range of conditions than previously imagined.
Take, for example, Europa, a moon of Jupiter covered in a thick shell of ice. Beneath this icy surface, scientists believe, lies a vast ocean of liquid water, potentially containing more water than all the oceans on Earth combined.
Or consider Enceladus, a moon of Saturn that has been observed spewing plumes of water vapor and organic molecules from its south polar region. These icy moons, once considered too cold and distant to support life, are now seen as potential havens for extraterrestrial organisms. Beyond communication, the search for biosignatures. The Drake equation, with its focus on detectable civilizations, inherently assumes that extraterrestrial life, if it exists, would be advanced enough to communicate across interstellar distances.
What if there are countless worlds teeming with microbial life, with ecosystems as rich and diverse as our own, yet devoid of any civilizations sending radio signals into the cosmos?
This is where the Seager equation, developed by astronomer Sarah Seager, comes into play. Unlike the Drake equation, which focuses on the probability of detecting intelligent life, the Seager equation focuses on the detection of biosignatures, any substance or phenomenon that provides scientific evidence of past or present life. This opens up a whole new realm of possibilities in our search for extraterrestrial life, allowing us to look beyond radio signals and search for the subtle fingerprints of life itself. The Seager equation, a new lens on life. The Seager equation, like the Drake equation, considers a series of factors that influence the likelihood of detecting life on other planets. However, instead of focusing on factors like the rate of star formation or the fraction of stars with planets, the Seager equation zeroes in on factors directly related to the detection of biosignatures.
One key factor is the number of stars bright enough to observe in detail, as this limits the pool of potential targets for our telescopes. Another factor is the fraction of these stars that have rocky planets within their habitable zones, as these planets are considered the most likely to harbor life as we know it.
The Seager equation also considers the fraction of these habitable planets that are observable by our telescopes, taking into account factors like the orientation of their orbits and the presence of any interfering factors. Finally, and perhaps most importantly, it considers the fraction of these observable planets that actually exhibit detectable biosignatures.
This last factor, the fraction of planets with detectable biosignatures, is perhaps the most uncertain and the most intriguing. It speaks to the fundamental question of how often life, once it emerges on a planet, leaves a detectable imprint on its environment.
Section 3. A universe teeming with possibilities. The Seager equation provides a framework for estimating the number of life-bearing planets detectable with current and future telescopes. Even with conservative estimates, the results are tantalizing. There could be dozens, if not hundreds, of planets with detectable biosignatures within our galaxy. These planets could harbor a staggering array of life forms, each with its own unique story. Finding even the simplest forms of life would fundamentally alter our understanding of our place in the cosmos. It would confirm that life is a fundamental force woven into the fabric of reality. The Seager equation offers a powerful new tool in our search for extraterrestrial life. Section 1, a paradox of silence. The universe is a vast expanse filled with billions of stars and likely even more planets. Equations like Drake's suggest that life should be common, yet a profound silence permeates the universe, contrasting the expected symphony of life.
This contradiction has led to the concept of the Great Filter, proposing improbable steps in the emergence of detectable civilizations.
These filters could be environmental, like the need for a stable star system or specific chemical elements necessary for life. Others might be biological, such as the leap from simple molecules to self-replicating life.
Still other filters might be technological, suggesting intelligent life might self-destruct through nuclear war or environmental degradation.
Section 2, filters of existence. The Great Filter theory doesn't solve the Fermi paradox, the question posed by Enrico Fermi, where is everybody? It suggests that the absence of detectable extraterrestrial civilizations might be a clue to the extraordinary challenges life faces.
If the Great Filter lies behind us, it implies we are among the fortunate few who have overcome a significant hurdle. Perhaps the emergence of life on Earth was an exceptionally rare event.
If the Great Filter lies ahead, it presents a sobering prospect. It suggests intelligent life might be extinguished by its own creations or cosmic events. The Great Filter theory serves as a reminder of the fragility of life. It compels us to tread carefully and strive for a future where we can overcome challenges, ensuring our species can continue to evolve and explore the vast cosmic ocean.